All right, so continuing the topic of improving developer experience, I'm here to talk today about the build and some of the investigations and work that we've done internally to try to make that a little bit faster. So first, a problem statement. And I think this is probably something that may resonate with many of you, but SONiC developers spend way too much time waiting for the build, thinking about the build, or trying to understand or debug it when it's not working. I took some data. This wasn't a very scientific study, but I went and looked at blog posts and other anecdotes, community messages, and found that it might be the case for the average SONiC developer that they're spending somewhere between a third and half of their time not working on the code that they want to write, but trying to figure out how to compile it. And this, quite frankly, is too much. So as far as the build, just to give a little bit of history, it used to be worse than it is now. And there are other anecdotes and blog posts and things through personal experience and other things where people complained about builds taking 12, 24 more hours in the last couple of years. And I want to give a lot of credit to the community members that have worked to make this better. As you can see, like on mainline today, it's 2 to 3 hours for most platforms to do a fresh build. And most developers have workflows that are well under an hour for incremental builds. But and to get there, like there's been a lot of stuff done. There are efforts to improve parallelization through the number of build jobs. There's just building the base images that you need, like skipping Jesse because nobody's building Debian 8 anymore. Improving caching and multiple layers, and then also adding like more robust mirrors to prevent build failures for upstream sources that weren't available. But all of that over time has also increased complexity, which makes it harder to debug problems when things go wrong. And so some of the challenges that we're starting to see is that from a performance perspective, it's harder to get those big wins. We're starting to see asymptotes forming on the build time. And the build is still too complex for many developers to understand when things are going wrong. And from an incremental build perspective, dependency tracking is still imperfect. So developers still need to understand enough about the build graph to know what to sort of remove so that when they do their rebuild, the bits that they're compiling are acting equivalent to the sources that they started with. So two parts to this in terms of the journey that we followed. One is a bottoms-up approach. So what can we do to just improve the component build times? And before I get there, we sort of asked the question, do we have a better build system than the current one? And the answer we found was yes. And the platform or the approach that we turned towards was Bazel. So for those of you familiar with Bazel, this will probably be repetitive, but for those not, Bazel is a build system that works with multiple languages. It does very fine-grained dependency tracking, which allows it to do considerably better in terms of caching and parallelization than most build systems. Hermeticity, or the ability to make sure that every time you run a build, you get the same output, is a first-class citizen, making builds extremely reproducible. And then there's a uniform build language. So once you learn how to write a build file, you can write build files for protobufs, for Java, for Python, for C++, Go, etc. And many of the improvements that we mentioned in the previous slides that we've seen in the SONiC community are already baked into Bazel from the start. Bazel has a full dependency tree, which enables massive parallelism, more parallelism than we can enable in the SONiC build today. And the hermeticity allows us to enable local and remote caches that enable at very fine-grained libraries or larger artifacts to be pre-available for other developers or CI systems. So what are some of the benefits that we've seen? One case study we'll look at today is moving from the existing make-based system to Bazel for Swiss. And before I get to the results, I just want to talk about what the Swiss CI pipeline or what the Swiss build is doing. The first thing we do is we start up a container and we download dependencies from the internet, like apt-get, pip, wget, etc. Pip's not a case for Swiss, but it's just for apt-get. Then we take the other dependencies that have been built within the system and we inject those into the container and install those as system dependencies. Then we build some binaries. Then we build the container image. We run some component tests, and then we store the artifacts. And one of the things that we found when we moved to Bazel is that when you apply a new build system within the existing SONiC framework, you're primarily able to cover the blue areas here. So build and test steps. we see that we can have cache hits that can improve performance, and we also get better parallelization because Bazel understands the dependencies at a finer grain level. So let's look at the results. In the top here, we have a build comparison using regular SONiC community build that we then layered some of the Bazel changes on top. And in the first line, in a system that we ran in our environment, we found that the existing build takes about 10 minutes to build Swiss. And the first half of that, roughly, is spent in the download, setup, install phase for the system dependencies. And then the second half of that is largely spent in the build and the build of the binaries, the Debian package, and the container. When we moved to Bazel, we found that there was a roughly 3x speedup, primarily because Bazel was able to better parallelize some of the build actions. And in this case, we turned off remote caching because it turns out if you have caching turned on, this Bazel build step is basically free. First, Bazel checks to see if the sources have changed. If they haven't, it's able to just download an artifact. But in cases where you actually have to do a build, we saw roughly 3x startup for the build phase. We saw a similar performance improvement on the test front. For building the Swiss component tests, roughly 20 minutes in the system that we were using, and we saw roughly 2.5 times speed up when we ran those tests through Bazel, primarily through parallelization again. So the question is this good enough? And we thought, probably not. So this forced us to take a step back and look at this problem from a different lens. And this required us to think about the top level build graph and what we could do to improve that to see if we could improve build performance. So I guess one key insight here is that gray part of the graph in our previous slide was fixed, and it's largely fixed for every single component. So this is the artifact download, dependency install, the overhead to set up the container environments, and then actually using Docker to do the builds. And so we were trying to think, what can we do to reduce that time? Because if we can reduce that time, we actually improve every component time. The second thing that we realized is that even with Bazel, caching is not really optimized in the context of building each of these individual components. N different Bazel instances means we need to really have N different Bazel caches, because system dependencies make cache sharing really hard, and it's possible that different versions of components could have different libraries that they're pulling in. So what this means is that we have a Swiss cache, a syncd cache, a cache for pins, every one of these components. So what can we do to actually drive this together so we have one big SONiC cache that can be shared so that when you're building Swiss or syncd, you're actually able to reuse a lot of the system type dependencies between them. So before we get into the solution, let's look at what the current state looks like. And SONiC today has a roughly 5-level build depending on your component. We have the top level build where the nodes of that graph are either Docker containers, Debian packages, Python wheels, etc. And then each of those nodes has a sub build that we invoke inside the build container, where we will do things like building libraries, depending on injected libraries, and then building Debian packages. So we go from a top level build into a component build for every single one of these components. When all of your dependencies at the top level build are satisfied, then your component can be scheduled. So the thought that we had is, what can we do to make this simpler? And for that, it means flattening this dependency graph. So instead of having high-level components and high-level build and component build, we have one unified build graph. What we can do is Bazel has a system called modules that we can use to reference other SONiC submodules. So that's part one, flatten the graph, have a unified Bazel that can look at all of the components at once. The second is try to avoid system dependencies wherever possible, because system dependencies are much harder to track and they get updated arbitrarily. But instead, what we can do is we can introduce these system dependencies, whether they're apt, pip, gomods, wget, etc., into Bazel, so Bazel is aware of them and can track when they're changed. The third thing we looked at is, instead of using Docker files to build containers, we actually can build containers using OCI image rules, which are part of Bazel. What we do is we create the tarballs that are required for each image layer as part of the build system, rather than relying on an external entity to spin up and run commands to get to the image that we need. And so we'll look at another case study here But what we found is that when we add these build files at the build image layer, we can actually do much better with caching and incremental builds. So here are the results. For building the Docker container for P4 runtime, and again, this is in our system using community SONiC with some modifications. We found that the build for the SONiC P4 runtime container was about 10 minutes in this environment. And we still had, in today's system, we still have the penalty of that 5 minutes roughly for setup, dependencies, and then Docker container builds at the end. In this case, we're just looking at a pre-populated build environment with everything but the component we're looking for. When we move to Bazel, what we found is that this gets really, really fast. We go from roughly 10 minutes to build the container to about 3 minutes in a case where you have no cache and you're starting from scratch. Once you've done that initial 3-minute thing, or if you happen to have a remote cache that has the artifact you need, we see incremental builds of both the binary and the container happening in roughly 5 seconds. In cases where you're making code changes and you want to do an incremental build, we're looking at like 12 seconds, maybe 20 seconds. But the point is that Bazel is able to very, very cleanly identify these are the pieces of the code that have changed and just go and run the GCC command on those few files, wrap them up into a bigger binary using shared libraries, and then put them into a tarball that becomes the layer for the Docker container. And so again, the numbers here are mostly just reflective of the relative performance that you'll start to see. A lot of the actual data that you'll experience in your builds is going to be dependent on the system you're running on and what caching you have available. But we're seeing roughly, somewhere in the order of maybe a 50 to 100x improvement for developers that are building containers using Bazel and a unified build graph compared to the traditional make-based system. So as far as next steps go, one of the things that we want to do for the community is define a best practice template for all SONiC container types. There's a different best practice for Python containers versus Go containers versus C++ containers. We also want to see if we can develop some migration tools, patterns, or instructions that can be used to help migrate all of the SONiC containers over to this approach. The second thing we want to do is publish some best practices for handling third-party dependencies. Things like app dependencies, pip dependencies, those are well thought out. But there are other dependencies that we have within SONiC for third-party libraries or binaries that we care about. And it may be more or less difficult to move some of them to Bazel. We know we can accommodate it. It's just a question of working on helping people do that. The third thing we want to look at is doing the SONiC final image assembly using Bazel. Most of the work we've done so far has been focused either on building binaries or building containers, but it's possible that we could extend this to the full image. And then we want to start contributing these build rules to SONiC. One cool thing about adding the new build system is that we can do it in parallel to the existing one. And if you want to run make, you can run make. If you want to run Bazel, you can run Bazel. Maintaining two build systems for an extended period of time is quite painful. But at least from a migration perspective, we can do this without disrupting the status quo. Over time, if the community accepts this, finds it useful, we can deprecate the old system without really any difficulty. So our goal, and this is maybe an aspirational goal at this point, but we want to see if we can get build times down to under 15 minutes from the 2 to 3 hours it takes today. Maybe we don't get there, but if we get close, I think any improvement will be helpful. The sub 1 minute container builds that we're seeing in incremental fashion is a promising start. But hopefully we can together get to a world where instead of that 1/3 to 50% of time, developers are spending 10% or less of their time focused on the build and the rest of the 90% focused on solving interesting problems. So, yeah, have a good day. Yeah, so if you have questions, you can go to the back. We have mics there. Go ahead.
Yeah, I believe the question here is, what about cross-compilation? Do you think about that? And will it be supported in your at least point of view?
Yeah, great question. So the cross-compilation. So one approach that we use today for cross-compilation is just building in the host architecture that we care about. That's been supported However, Bazel does have cross-compilation support. So actually, one cool thing about Bazel is that from a toolchain perspective, you can do whatever, you can use any toolchain you want. It doesn't have to match the toolchain that's present on your host. So we definitely, as part of this work, want to test at least x86 and ARM architectures and cross-compiling into those. But some of that depends on how well supported the toolchains are for cross-compilation. C++ and Go seem to be pretty well supported, but if you have other languages, it sort of depends on both the toolchain support for cross-compilation as well as somebody, a maintainer of the Bazel rules, how much they've done to do that. But it should certainly be possible.
And maybe like a second part of that, currently there is a big part of the SONiC, which is Debian, being downloaded from the upstream repos, and there is a huge work done in SONiC now to make the reproducible build. Will this be inherited somehow, or there will be another way how we will do it through Bazel?
So I think the general principle that Bazel has is build everything from source. And one of the ways it helps people achieve that effectively is by leveraging the hermeticity guarantees allow for aggressive caching, whether that's locally on your system or in a remote cache. As far as and I think a lot of users probably want the ability to have the source so they can rebuild the components they care about. Because even the things that you think we download from the internet, like there may be some people that actually want to modify that component, like the Linux kernel, for example, or the binaries that you get from your vendor. So what I would say is that the way that most teams are going to benefit from improved performance is probably by hosting remote caches that are local to their company or to their environment. We may be able to host some remote caches for CI systems, for example, just to improve builds in Azure. But the caching mechanisms look different because instead of downloading like an apt package from a mirror, we can talk a little bit more about the details later. So we may be able to reuse some of the mechanisms, but there also will be some new ones.
Thank you.
Yep.
Yeah, thanks. It's a very nice result, and also the goal is very clean and ambitious. So Li Hua mentioned this one to me before, so it's very nice. So I'm wondering, like, because today the SONiC builder working group is dead, so there's nobody there at all. So do you thinking like maybe like Microsoft, Google, and Alibaba will partner together, that's reviving that working group? So
yeah,
we can...
Sure. Yeah, I think that would be great. And we can respond to Michael's call to action by reactivating the group. I think we're getting to a point now where we can start to share some of the best practices and get feedback from the community. So yeah, if there's interest here in a build working group, we should definitely get that going again.
Yeah, that'd be great.
Yeah, thanks, Eddie.
Thanks.
I have a question here. Thanks, Brian. Good presentation. So you mentioned build and test as well, right? So today's tests are all part of the Azure pipeline as part of the repos. So is that like within the context of that, or are you thinking those pipeline workflow files need to also evolve to accommodate?
Yeah, that's a great question. And we talk about tests, we talk about many layers, right? At the lowest level, we have unit tests, we have component tests, we have end-to-end tests that run on a single device, perhaps, and then we have fabric tests, right? And so I think the scope of tests that I'm talking about in the context of the work we've done so far has been unit and component tests, primarily just, software tests that's testing in software without the context of a full image. Could we go further? Quite possibly. And that would be an interesting thing for us to explore as a group. But today, the workflows that we have for doing the system type testing are kind of a different system. So, but we could look at certainly doing that. Fundamentally, Bazel is basically Python rules that allow you to have inputs and execute outputs and track dependencies. So we could certainly run a broader set of tests in that way, although it would probably require some work to set it up. But yeah, we're focused primarily unit and components for now. Yeah, one more question.
Hi. I wonder, like, maybe this is a little bit jumping ahead of ourselves, but like, does Bazel naturally lead to the next question of like establishing build farms or test farms? Because like, does it make it more efficient, and have to think about it?
Yeah, that's a great question. So does Bazel change the way that we do CI builds? It could. So Bazel is designed to work just in a single laptop or VM, and it works efficiently in that mode for most developers. But if you want, it does support something called remote build execution, or RBE, and that model or mode would allow you potentially to set up a build farm where a CI system could kick off a job to dozens or more machines to increase parallelism. In this case, it's not entirely clear to me whether that type of infrastructure will be necessary, given how fast we're seeing things. But if you are setting up, a CI system, that is certainly an option where you could set that up. And as long as you have a hermetic environment that doesn't require on system dependencies, that should work fairly seamlessly.
Okay, thank you.
Yeah. Okay. Thank you.